Welcome to today's GATE class. Myself M.RAMALATHA, Assistant Professor, Department of Mathematics, S.A.E. Engineering College. Today's topic is singular decomposition from linear algebra. Okay, before move on to our topic, we have some basic knowledge about this topic. What are the basic knowledges? Means, suppose you're going to use the concept, means the concept is where it is working, how it is working, why we use this. These are the things you're going to be know. Because of that, we know in depth, it is not a matter here. You're going to just basically you know the concepts, because in our topic singular decomposition, what is singular, what is decomposition, why the singular is going to be decomposition. So listen, nowadays these are the things we use frequently. It is a technology. What are the technologies here? Data analysis, signal processing, image compression, machine learning. These are the things nowadays we frequently use in all the core papers, wherever it is in a world is built. Nowadays the built by these applications here. So how it is SVD working here? SVD is nothing but singular decomposition. So how the singular decomposition work in this topics? First, see, suppose you're going to take a signal processing. For example, you're going to take a signal processing. Just you know what signal processing there. Where is the signal processing working? In a railway. Important, it is a railway. Railway, suppose the gate is going to be open, means the signal is come from the before station, then only the gate keeper is going to be open the gate, otherwise it can't open the gate. Is it correct or not? So the signal, it comes in a proper way, correct time, then only the gatekeeper is going to be close the gate or open the door. Is it correct or not? So that's why how it is working here SVD. So signal not come with only with that correct form, it along with some noise. So the noise is the extra fitting, the noise is anonymous here. So you're going to be decompose. What are the part you want? Take that part for your reach the gatekeeper. The remaining part is going to be erase or decompose or go to the equilibrium point or go to the rest. So here the signal is the important thing, main thing that going to be reach the gatekeeper. The noise is going to be removed or decomposed. Then how that for this thing the SVD is working, that we're going to assume that noise is, it becomes zero. So here that singular, listen here, the singular decomposition, singular. So you people know about matrix. Okay, that word is the singular non-singular word is used in matrix only. Then what is singular, what is non-singular here? Singular, non-singular is nothing but suppose you're going to assume a matrix here. See here, the matrix is here. We're going to assume a matrix. Here one matrix is there. In our problem one matrix is there. Because already in our topics, the topic main heading is singular. So our matrix is a singular matrix. It is going to be decomposed. Suppose what is this non-singular? Non-singular, that what are the difference between singular and non-singular? Here you see, you know that matrix are basically 11th to 12th. You people studied about that singular, non-singular. So what is singular, what is non-singular? Listen, first you're going to be find the determinant of the given matrix. Listen here. What is the determinant of this given matrix? 2, 2, minus 2, 2, 2, minus 2, minus 2, minus 2, 6. This is this in between two straight line going to put the values. It is a determinant. Is it correct or not? So that's why this implies how to find the value of this 2 into. First you're going to take either any row, any column. You're going to find the determinant of the matrix. First I'm going to choose this first matrix. So hide that first row, first column. What are the things? 2 into 6, 12. Minus 2 into minus 2, plus 4. But then the form it is a minus 4. Then after the second value, minus 2 into, it is a procedure. It is a determinant procedure only. Minus 2 into, hide that column. Wherever the element present, you just hide that column and row. The remaining you're going to be multiply. 2 into 6 is equal to 12. Minus 2 into minus 2 plus 4 minus 4 it becomes. Then after third already it is minus, but in the procedure it is a plus, but the element is minus, so that's why you're going to take it as minus 2. Then after hide whatever the element is present here, means you guide the row and column. Then after get the multiplication. 2 into minus 2 minus 4 minus 2 into plus 2 minus 4. In the formula it is a minus, though it becomes, what is it? You're going to cancel these two things, it becomes the value, it becomes 0. So our determinant, our given matrix determinant is equal to 0 means, our determinant, given matrix determinant is equal to 0 means, then only going to be said that matrix is a singular matrix. Suppose now choose another one matrix. See here, this is suppose, for example 1 0 2 0 1 3 4 5 6. Here consider this matrix. For this matrix you are going to find the determinant. What is the determinant of this? The same similar only. 1 first element on either row or column. 1 into 6 6, 5 3s are minus 15, plus the second value automatically it becomes 0. Whatever it is, it becomes 0 because of the element is 0 means the total values it becomes 0. The element is present, you're going to hide the column and row, the remaining element is going to multiply. 0 into 6 is 0, 4 3s are minus 12. Then after minus 2 into hide the 2, the row and column, then after 0 minus 4. Then what is the value of this? 6 minus 15, what is the answer? 6 minus 15, it becomes minus 9. Then after minus 2 into minus 4, the remaining all are become 0 because 0 into something 0. Then after minus 2 into minus 4, it becomes plus 8. The answer is equal to minus 1, not equal to 0. Here the determinant of this matrix is not equal to 0. Here the determinant of this matrix is equal to 0. So this matrix determinant is equal to 0. This matrix determinant is not equal to 0. So according to this, the determinant of the given matrix determinant is equal to 0 means it's going to be tell that matrix is singular. Not equal to 0, going to tell it is a non-singular matrix. This is non-singular matrix. Okay, so that's why here in the non-singular matrix we don't have any problem. We use direct methods. A lot of direct method is here to find the solutions and how to compress it. Very easy. The direct method is nothing but Gauss elimination method, Gauss Jordan method, because it has an inverse. Our singular matrix don't have an inverse, because why it don't have an inverse means the columns are linearly dependent. Here the columns are not linearly dependent. Here the columns are linear. What is linearly dependent here? Sum of the columns is similar to some columns, or otherwise it's an expression of any other column. Here you see the first, this two columns, the 1 and 2 columns are same. The 1 and 2 columns are same means it is linearly dependent because 2 are similar here. The columns, any of the columns are similar here means the rank of the matrix is going to be reduced. So the reduced word is nothing but another one word is decomposed. Automatically the rank is going to be reduced. So it means that one of the eigenvalue or more than an eigenvalue, it's going to be 0. Here 3 eigenvalues are 3 cross 3 matrix means we have 3 eigenvalues. The solution, if you solve the equation, suppose you're going to be solve the quadratic equation. Suppose you're going to be solve the quadratic equation, x square minus 2x plus 3 is equal to 0, some quadratic equation here. How many solutions for this quadratic equation? You have two, because of the highest order of the x is 2 here. So that's why you have 2 solutions here, you know. The same similar here. Here the matrix is 3 cross 3 matrix. So that's why how many solution for this matrix? 3 solution for this matrix. 3 that is solution we going to be use the word eigenvalues. 3 eigenvalues. So 3 eigenvalues. Suppose the columns are linearly dependent. The singular matrix, the columns are linearly dependent. Linearly dependent means we don't get proper 3 eigenvalues. Any of the eigenvalues is going to be 0. Any of the eigenvalue is going to be 0. So now you come on to the signal processing here. In that signal processing, we want only signal, but now the signal not reach the gatekeeper, but the sum of the noise, anonymous noise along with that signal. So that this SVD is going to be remove that whatever unwanted part. The unwanted part is going to be removed, or it going to be set it as equilibrium or 0. Equilibrium 0 or rest. So that's why for that type of process you're going to be use SVD, because here the agent value, any of the agent value, it move on to 0 means you're going to be the projection not in that axis. Okay, 3 things is here means you're going to be the projection is 3 directions, but here 1 agent value or 2 agent value it's going to be 0 means the projection is not in that side direction, it going to be keep it as rest, but the value is there means that value side only, that direction only is going to be the projection is performed. So the signal system, signal processing, data analysis, image, the another one is image processing. What is image processing here? Image processing means you have an image but you don't want some unwanted part, then how to compress it? Because of that all know nowadays, you know, Android phones, tab, laptop, system monitor, whatever it is, all the hardware background is a grid line. Is it correct or not? Grid line is nothing but an array. The data is going to be stored as a byte or bit. It is a rectangular array. The rectangular array is nothing but a matrix. If you use anything for that, nowadays the systems now, smart phones, whatever it is, all the things are going to be stored in the background is nothing but a rectangular array by using bits and bytes. It is a matrix. The value, the way that whatever the data you're going to be input, the inputs are going to be saved it as a matrix in an array. So that grid lines, is it correct or not? So in that grid lines, which part you don't want, the same thing, it is like the column. Grid lines means like that only, is it correct? It is a rectangular array. Suppose I don't want this part, I don't want this part, I don't want this part means this SVD is going to be compressed. This SVD is going to be rest that part. So we consider that agent value is 0. That agent value is 0. So image processing. So in image quality you want, the originality you want, but you don't want the unwanted part. This SVD perform there also is going to be remove the unwanted part or keep that as rest and give the proper image to you. So image processing, signal processing, whatever it is, this process is the SVD bag work is lot here. So now move on to the problem. Now move on to our topic here. See here. So listen, singular now. See here, what is singular decomposition? Singular value decomposition, SVD is a matrix factorization. Because it's a singular matrix, we don't use the direct method like Gauss elimination, Gauss Jordan like that. So that's why you're going to be use only matrix factorization here, because we don't use the original matrix here, we use the orthogonal of this matrix, because the original matrix automatically, you know, sum of the agent value it becomes 0 means sum of the part is lost. Sum of the part is lost means you don't know the originality of the given problem or given process. So that's why here you're going to be use matrix factorization technique that represent the given matrix A as a product of 3 matrices U, E, V, T. U is nothing but agent that first is going to be solved. The first you're going to find the orthogonal matrix. For that orthogonal matrix, you're going to find agent values. The 3 cross 3 matrix means going to get 3 agent values. For our given matrix, we don't get 3 proper agent values because some of the values is going to be 0. So that's why in here going to form an orthogonal matrix A transpose. Orthogonal matrix is nothing but A transpose here. Okay, A transpose is an orthogonal matrix. It's an orthogonal matrix. Orthogonal matrix. So our going to be change our given matrix A, because it's a singular matrix, some of the agent values are 0, so it is nothing but in a common word, some of the data are missing, some of the data are lost. In one direction or 2 direction, the projection is don't have. So that's why which direction don't want the projection. First you're going to be identify by using this procedure here. So that's why first you're going to form the given matrix as an orthogonal matrix A transpose. So then after you're going to find then you going to find U, E and V transpose. Then how you find VU? First you are going to get 3 eigenvalues. For this 3 eigenvalues, you are going to get 3 eigenvectors. By using the 3 eigenvectors, you are going to form U. The transpose of U is nothing but V transpose. E is nothing but the 3 eigenvalues. It is a diagonal matrix. The positive values. That the E matrix is a diagonal matrix with non-negative elements are called singular values. That singular values is nothing but eigenvalues here. Okay, what are the eigenvalue for A transpose? That A for normal matrix is going to find eigenvalue means it is a eigenvalue. But we don't get the given matrix as a eigenvalue, so that's why going to be changed it as A transpose. That's why we use the word singular values. It is non-negative only. By using the 3 non-negative singular value in the diagonal is nothing but E. By using this 3 matrix, you are going to be perform SVD here. Already we know, we saw this slides, where it is used, how it is used, why it is used. These 3 things I explained in the first initially. I explained these 3 things only here. One is data analysis. Data, what are the data you want means you take that data only, the remaining unwanted part is going to be removed by using SVD. Going to be decompose the data. That are going to be set it as rest or equilibrium points. Then signal processing. That signal not come along with only a signal, it also along with a noise. You don't want that noise, so you're going to remove that noise, going to keep it as rest. That's why the eigenvalue is 0 there. Then after image compression, then after machine learning. These are the now our core papers. In engineering field, it is a very important topics here. In that important topic, SVD works, how it is. Initially I explained you. One of the most important application of SVD is ability to reduce the dimension. That what is a dimension means that what are the part you don't want means you know it is a gray line. It is a green line. Is it correct or not? Suppose I don't want this part. I don't want this part. I don't want this part means automatically the dimension is, it is a dimension of, what is it? 1, 2, 3, 4, 1, 2, 3. 4 cross 1, 2, 3. 3 cross 4. Is it correct or not? The dimension is, suppose I don't want this means, I don't want this means, these are the things arrays is going to be cut from, decomposed from this. The dimension is automatically is going to be, the dimension is automatically going to be, what is it? 2 cross 3. Is it clear? So dimension. So it is a dimensionality of a data set while preserving most of its important feature. Reduce. Whatever the data items you don't want means you remove from the item from your background. That is whatever this monitor you use. So it is going to be compressed without don't want data. That anonymous data is going to be reduced by using SVD here. So this is the achieved discarding the smaller singular values and their corresponding columns of U and V matrices. Listen, the process of computing SVD, what are the things we are going to be use? First of all, you take one matrix, singular matrix here. The singular matrix row and column, either it is a rectangular array. Suppose you are going to M cross N is nothing but what is it? M is 3, N is 4 like that. Whatever it is, square matrix also it's we going to be used. Now we use only square matrix here, 3 rows, 3 columns here. Then what are you going to do here? First you are going to be frame a orthogonal. Orthogonal is nothing but A transpose or A transpose or A transpose A. These two things are orthogonal. A transpose is nothing but what? You are going to change the row, interchange the row and column is nothing but A transpose. Already we have A. We are going to multiply, make a product, you get that orthogonal matrix. By using that orthogonal matrix, you are going to find eigenvalues. For the corresponding eigenvalues, you are going to find the eigenvectors. Okay. By using that eigenvectors, you form U and V here. Listen, the process of computing SVD involves the following steps. The SVD, already we see 4 steps. This is the 5th step here. Listen here. The SVD of A is the triplet. Triplet means already I explained you. U is nothing but orthogonal matrix A. By using these 3 eigenvalues, you are going to get 3 eigenvectors. By using the 3 eigenvectors, you form U. The transpose of U is nothing but V transpose. This is the diagonal matrix. Sigma is nothing but a diagonal matrix. By using eigenvalues, here you use the word not eigenvalue. It is a singular values. Okay. Here SVD can be computed using various numerical methods such as power iteration, Jacobi method. This is an indirect method. We can't use for singular matrix. Direct method we can't use. Only indirect methods or factorization method is going to be used. The SVD is the factorization method. You have some indirect method also. The indirect method is nothing but power iteration method, Jacobi method. Power, that is, it is an iteration. You are going to choose some initial value. By using the initial value, you are going to use the, it is not an accurate value, it is an approximate value only. Okay, indirect method you are going to get only approximate value only. The method used depends on the properties of the matrix being decomposed and the desired computational efficiency. Suppose according to the matrix, what method you are going to be used, you are going to be suggest. Because the data, whatever the method you are going to be used, the data, the solution, the accurate result not affect. That is the thing here. Now you move on to the problem here. Now this is our problem. What is our problem here? 2, 2, minus 2, 2, 2, minus 2, then minus 2, minus 2, 6 here. See here, it is a singular matrix here. This first and second column are both are similar. The similar, already I explained you what is singular. The columns are linearly dependent. Linearly dependent means some of the columns are similar or some of the columns are expressed by using the another column. That is called linearly dependent. Columns are linearly dependent. Going to tell the matrix is a singular matrix here. Okay. Isn't it? Here the same thing only. The let A, B, M cross N matrix. Here 3 cross 3. M is 3, N is 3. Okay. Orthogonal matrix. First you are going to form an orthogonal matrix. By using the orthogonal matrix, you find UV and diagonal matrix and going to form this thing. You are going to get the answer of the given singular matrix. We are the side. Third column is our first two elements. First row, first column, first element. First row, second column, second element. First row, third column, third element. Similarly, second row, first column, second row, second column, second row, third column, you are going to get second row all the three elements. Similarly, the third row, first column, third row, second column, third row, third column, you are going to get third row all the three elements here. After going to be processed the product, you are going to get this matrix. A transpose A, 12, this matrix is going to get among all the 9 elements, 4 is common. Among all the elements, 4 is common. So going to take out the 4, then you're going to get to 3, for this 12, 3, minus 5, 3, 3, minus 5, minus 5, minus 5, 11 here. Okay, you're going to be considered. Listen, let us consider the matrix as, because of that the common part you're going to be take out, only use the matrix here. Okay, because that 4 is common, so that's why remove that 4. You're going to take the matrix only for the procedure here. So the matrix only is nothing but what is it? 3, 3, minus 5, 3, 3, minus 5, minus 5, minus 5, 11. You're going to consider it as a B matrix. Okay, for this B matrix you're going to find eigenvalues and eigenvectors. Listen. First you are going for 3 cross 3 matrix is going to form a characteristic equation. Then 3 cross 3 matrix means what is the characteristic equation? This is the general formula for 3 cross 3 equation. Lambda cube minus S1 lambda squared plus S2 lambda minus S3 is equal to 0. Okay, listen. What is S1? S1 is nothing but main diagonal element. What is our main diagonal element? 3 plus 3 plus 11 is nothing but our main diagonal element. It becomes 17. Then what is S2? What is nothing but S2 is nothing but the main diagonal determinant values. Okay, minor values. Main diagonal minor values. For 3, first one is 3. For 3, what is the minor element? 3 minus 5 minus 5, 11. You're going to take here. Then second, what is our second diagonal element? 3. Hide that element, row and column. So second column, second row, you're going to hide what you get. 3 minus 5 minus 5, 11. Then third one, third minor. So this is the third eigenvalue, the diagonal element. You're going to hide this element. Third row, third column, you're going to get 3, 3, 3, 3. So you solve this. 3 into 11, 33 minus 25 plus 25. That form it is minus 25. Then after 3 into 11, 33 minus 5 into minus 5 plus 25. But in our formula it is minus. Then after 3 into 3, 9 minus 3 into 3, 9. You solve, you're going to get 16 is nothing but S2. Then see here, S3 is nothing but determinant. Already you know the determinant value is 0. So already I solve in that, initially I solved this. So S3 is equal to 0. Now you know S1, S2, S3. Then listen. Now our characteristic equation of our given matrix A transpose, we are going to take on the A transpose is nothing but B. For that matrix, we are going to use this characteristic equation, lambda cube minus 17 lambda square plus 16 lambda is equal to 0. One value is going to be erased automatically. So it is decomposed automatically. Listen here. You solve this equation, what you get? One value it becomes 0. Is it a singular matrix? Two columns are linearly dependent here. So that's why. So solve this square equation, you're going to get 1 and 16 as a eigenvalue. That is root. The eigenvalue is nothing but a root only. You solve this equation, you're going to get 0, 1, 16 is the eigenvalue here. For this eigenvalue, you're going to find eigenvectors. Okay. Listen here. Because of that, listen. That original matrix A transpose A is nothing but what? 4B. For this B only, we are going to find this 3 eigenvalue. So that's why 4 into, so here 4 into 0, 1, 16. You multiply, what you get here? So 4 into 0, 0. 4 into 1, 4, 4 into 16, 64. So original A transpose A is equal to 4B. So that's why you're going to get 0, 4, 64 is our eigenvalue. Listen, you now going to find the eigenvectors. Order of the vectors come from the singular value largest to smallest. First largest, lambda 1 is equal to 64, 4, then after 0. By using this vector eigenvalue, you're going to find, first you're going to form a eigenvectors, that is this equation formation going to be get the eigenvectors. What is our matrix here? A transpose A, it's our matrix now, minus lambda into I. Lambda is nothing but a eigenvalue, I is nothing but identity matrix here. Okay, listen here. Here we're going to perform like this only. Okay, see here. So that's why what is our lambda here? Our lambda is 64, first lambda. You're going to take this first lambda. This first lambda is going to be take here now. Okay, what is our first lambda? 12 minus 64. 12 minus 20. 12 minus 64 minus 20. So minus 20 minus 20, 44 minus 64. Then after going to take x is nothing but how many eigenvalues is here? 3 eigenvalues is here. So that's why going to take 3 eigenvectors. It's nothing but what is it? x1, x2, x3. So 0, 0, 0. Now you solve this and multiply. Here one row, you have a 3 rows. Here listen here. 3 into 3 here 3 into 1. So what you get? So you're going to be combine this two. The resulting matrix is nothing but 3 into 1. So only one column matrix is going to be hit here. So now see here. 12 minus whatever I taught you, the same thing here. Going to minus, you get that matrix. Then after perform multiplication, then you going to get the equation. Okay. That is going to be common term is here. You're going to take the common value out. That is what is our common value here? 4. You're going to take 4 outside, means you're going to get the minus 13x1 plus 3x squared plus minus 5x cube is equal to 0. So that nothing but next equation. Similarly next equation. Then we're going to be solve this equation. First row, first column, second row, second column, third row, third column here. Here two things are identical. So that's why here listen here. So that's why listen here. For x1, you guys hide the x1. Then after use this 4 elements to find here. Okay, what is the 4 elements here? 3 minus 5 minus 13 5. For x2, hide this x2 is going to be right. Minus 13 minus 5. 13 minus 5. Then after you're going to be hide, you're going to write the element. What is the element? Minus 3, minus 13, 3, 3, minus 13 you're going to. Now you're going to make a cross multiplication here. Listen. 3 into minus 15, minus 15, minus 15 into minus 13, minus 65. Similarly, you're going to take 2, 2. Minus 5 into 3. Minus 13 into minus 5 into minus 13. Then after minus 13 into minus 13, 3 into 3. Going to get the result. Finally, going to get the single value of the given value x1, x2, x3. So x1 by minus 80, x2 by minus 80, x3 by minus 80 all have a common value 80. So divided by 80 you're going to get minus 80. Going to divide by minus 80, 1 comma 1 comma minus 2. So listen. So you're going to be divide by minus 1, it's no problem here. Listen here. Minus 1 comma 2. See here. So norm is nothing but you take a square of the given value, take square root of the values of the square. So minus root of minus 1 the whole square plus minus 1 the whole square plus 2 square. What is the value? 1 plus 1 plus 1 plus 4 is equal to root 6. Isn't here? For this normal vectors, normal eigenvalue, minus 1 by root 6, minus 1 by root 6, then 2 by root 6. Already I tell you, you're going to be, here you're going to be change here also. Common minus you're going to take out the same similar it becomes here. Okay, so you're going to be normal vector, you normalize the vector, eigenvector you want means you divide the value by norm value. What is our norm value? Root 6. What is the here? Divided by root 6. The same similar should come here. That's enough. Okay. Similarly you're going to find remaining two vectors. Now my next value is minus 4. The same the general matrix is there. In the general matrix, you're going to be change the lambda value. Second value is 4. So second value you're going to substitute to get that matrix. Then after perform, you're going to get three equations here. You take any two of the equation and solve. You're going to get the matrix eigenvectors here. See here for x1 what is the things 3 minus 5 2 minus 5. For the x2 what is 2 3. Then after minus 5 2 minus 5 3. Then after for x3 what you get 2 3 3 2. Then solve this, you're going to get x1. That will make a cross multiplication only here. This cross multiplication only here. This cross multiplication. What is this cross multiplication? Second term, this cross multiplication. Then 3 into minus 5 minus 15, 2 into minus 5 plus 10. Okay, like that you're going to be solve. x1 divided by minus 5, x2 divided by minus 5, x3 divided by minus 5. So that's why you're going to get x2 is equal to, so all have minus, common minus, so that's why you divide by common minus. So minus 5 1 1 1. So the eigenvector is nothing but, second eigenvector is nothing but 1 1. For this, what is the norm of this? What is the norm of this? What is the norm of this? Means root of 1 squared plus 1 squared plus 1 square, you're going to get root 3. So normalized vector of x2 is nothing but what? You're going to be divide this by norm value. 1 by root 6, sorry 1 by root 3, 1 by root 3, 1 by root 3. This is our second agent. This is our exit. This is second normalized eigenvector here. Okay, see. The same thing now you see here. What we done before, the same thing here only v2. This is the second normalized vector. Similarly, going to get third normalized vector. Because third value is 0. So 0 you're going to minus the 0, same matrix only become here. To solve this, you're going to get, we want only two equations. So that's why two equation is enough here. So that's why solve this two equation, you're going to get third eigenvector. Similarly like this. See here. Then it's just the same cross multiplication, 3 into 11 minus 5 into minus 5, then minus 5 into minus 5, 11 into 3, 3 into minus 5 minus 5 into 3 going to get. Now you solve this, you're going to get the third eigenvector. Yeah. 8 minus 8 0 divided by 8, you're going to get 1 minus 1 0. So 1 minus 1 0. What is the norm of this? Norm is nothing but root of 1 squared minus 1 squared plus 0 root 2. So divided by root 2, you're going to get a v3. That is normalized vector v3 here. v3 not v2. So okay, that's fine. See here. So So here that E is nothing but, since A is symmetric matrix we have. So symmetric means the upper triangular element and lower triangular element both are same, means that matrix is nothing but a symmetric matrix here. So that's a symmetric matrix is nothing but U and V are same here. So you're going to write directly our eigenvalue as the root of the diagonal element. So E is equal to root of lambda 1, root of lambda 2, root of lambda 3. Our first eigenvalue is 64, second eigenvalue is 4, third eigenvalue is 0. So what you get? 8, 2, 0. This is E. Already you know V. Now you form the singular decomposition. That first normalized vector for x1, second normalized vector for x2, third normalized vector for x3. Okay, is nothing but U. Then after you know E is a diagonal matrix. Then after V transpose of this matrix, transpose, see here the row and column is here. Okay, see here. So you solve this, you're going to get the decomposition here. So this is the process of this U. U is nothing but the eigenvalue by using, going to find the eigenvector. For that eigenvector you're going to find the norms, form normalized vector. By using the normalized vector you're going to form this. Okay. Then after you're going to take a transpose of V transpose, you're going to get V transpose. Already this one is nothing but a diagonal matrix. You're going to multiply this 2, 3, you're going to get one answer. That answer is nothing but a compressed, decomposed matrix of the given singular matrix. Thank you. If you have any doubt means you ask me. We will continue in the next section.